to calculate the decay rate if your atoms undergo a radioactive decay. This is actually the only equation to actually memorize. So this is actually the integrated rate law for the first order reaction. A naught represents the initial concentration of your atom. AT is a concentration of atom at time t. K is actually just your rate constant. And T just time. The typical problems you're going to see is that, so it says a first order reaction is 35% complete at the end of 55 minutes. What is the value of K? We are going to use the natural log AT over A naught equals to negative KT. Don't forget the negative sign. The T is going to equals to 55 minutes. And then it says the reaction is actually 35% complete. You should be able to translate 35% complete. That means actually 35% of your original atom has been consumed. But here is actually you want to know the concentration of atom at time t. So you consume 35% of the atom. That means actually your AT is actually going to be original concentration times 65%. So that's a very important translation you need to do. You doesn't care about how many things are consumed. This equation only care about how much of the reactants I still have at this specific time. Since this says okay, the reaction actually is 35% complete. What it really want to say is actually there's still 65% of the reactant remains. So you need to know your AT is equals to your 0.65 A naught. So once you have this, then you can just put these things inside this equation. Okay, your AT is 0.65 A naught. Origin concentration is actually A naught equals to negative K times T is actually 55. So A naught cancel out. By doing this calculation, you should see your K is going to equals to negative log, natural log, 0.65 divided by 55. And then you're going to get a value of 7.8 times 10 to the negative 3 minutes. The keyword is actually, if you see this word complete, you want to actually translate into the situation that have the information of how many of the reactant remains. Okay, so those are the part that students always get confused. So let's look at another way to actually ask the same type of questions. A sample of aluminum-32 is found to have activity of 400, and after 10 hours, its activity has decayed to 200. What is the rate constant for this decay? So every time you see this decay type of questions, there's actually only one equation to go to, right? Natural log AT over A naught equals to negative K times T. The information clearly shows up is actually 10 hours, right? So you know you have your T here. You want to actually looking for your K. That means actually to first figure out your AT over A naught. Here it actually says in the beginning, you have activity of 400. That means actually your reactant itself is going to provide 400 activity. After 10 hours, you still have 200 activity. So you can use that activity as an indication of how many original reactant you still have. That means after 10 hours, your AT is going to equals to 200, but your A naught is equals to 400. Therefore, if you put these two information back to here, it will be natural log 200 over 400. It's going to equal to negative K times your T is 10 hours. Therefore, your K is going to equal to negative natural log 0.5 divided by 10. Therefore, you're going to get a value of 0.693 per hour. So you should notice that the unit you got is actually going to associate with the unit you put in. So if your T here use hours, then it becomes per hours. If you use minutes, it becomes per minute. Okay? So that's pretty much the standard questions you're going to encounter when you calculate the decay kinetics. The important thing is actually you don't care about how much of the reaction complete. All you care about is actually how many reactant remains. Then you can apply the first order integrated rate law to get the correct answer. Let's talk about the thermodynamic stability of the nucleus. The first concept we're going to introduce is actually you need to know how to calculate these things called the mass defect. Mass defect was defined as the difference between actual and hypothetical weight of your atom. For example, so helium-24 has actual mass of 4.0015 AMU. And then you want you to calculate the mass defect. This is actually one of the type of questions you're going to see a lot in this chapter. The questions provide you a actual mass of this specific atom. But from here, you can also calculate the hypothetical mass of this atom, because here you know there's actually 2 protons and then 2 neutrons from this atomic symbol. So in the very beginning of this chapter, you can see on the rightmost column, they say it's a thing called the AMU, right? Atomic mass unit. That actually tells you if you have 1 neutron, it actually contributes to that much atomic mass unit. In principle, if you actually use the number of neutrons multiply this value plus number of protons multiply that values, you actually be able to calculate the mass in the unit of atomic mass unit for every single atom. So that's the things we're going to do here. So for 1 single proton, its mass is actually 1.007825 atomic mass unit, 1.008665. So if you calculate this, you should be able to get the mass, the hypothetical mass of your helium-4, okay? It should be equals to 4.0329 AMU. But if you compare this hypothetical mass to the actual mass, you'll realize they are not exactly the same. There are some differences between the 2 mass, right? And that difference is so-called the mass defect, okay? So the mass defect is simply equals to 4.0329 minus 4.0015. Then you're going to get a value of 0.03148 AMU. Okay, so that's actually so-called the mass defect. So this mass defect, eventually you see some mass loss, right? So where do you go? It actually convert to some energy and release to the surrounding. That is actually why you need to know all these different decays, right? Because those are the ways that they are going to release the energy, and then the cost of that releasing energy comes from the mass loss. The equation that combines these 2 things together is the most famous equation. So this is actually the things that connect the mass defect to the energy. E equals to mc squared, and then you can write this delta E equals to delta M times c squared. Delta M is actually the mass defect that you can just calculate it. C is a speed of light, and then it's going to be a constant 2.99 times 10 to the 8th power meter per second. Again, these things will be provided. So you don't need to actually memorize this value, but you need to know the C is actually the speed of light. The delta M need to have a unit of kilogram, so that your delta E has a unit of joule. So right now the things you calculate is actually, you know the mass defect is 0.03148 AMU. So that's not kilogram. So before you can actually put this number in here, you need to actually do one more conversion. So 1 AMU is going to equals to 1.66 times 10 to the negative 27 kilogram. This will be provided, but you need to do this conversion before you can plug it into the equation. With all the things in mind, then you know your delta E for this case, it's going to equals to your delta M is 0.03148. This is AMU, right? You want to convert into kilograms, so you need to multiply 1.66 times 10 to the negative 27. Okay, so this will actually give you the mass in kilogram. And then you need to actually multiply your speed of light, 2.99 times 10 to the 8th power. Don't forget to square it. So once you put these things all correctly, then you are going to get a number of 4.39 times 10 to the negative 12 joule. Okay, and those are the binding energy of that mass original actually existing on your atom. When they lost it, this is how much energy they are going to release. And that's actually how you associate your mass defect to the binding energy of the mass.